we'll start with a new set of problems. So that is the problems on trusses. So using a truss element, we will be solving the problem in an ANSYS APDL. So for that, so this is the definition of the problem, wherein there are 4 truss elements and they are fixed at 2 points at this region where I am highlighting with the cursor and at this region. And the cross section area of each truss member is 0.1 meter square and the Young's modulus is 210 GPa, that is gigapascal, and he has given the length of the truss elements. So, and also there is another different condition, you can see it here, which is the roller. Okay, so this is a roller here, roller support is there. So with all this information, we'll start with the ANSYS. So I'll go to the ANSYS window. Here I can save the file as, so it is a 4-bar truss member. Four-bar truss member. Okay, and it is a 4-bar truss member .db. So I'll say okay. So once you do that one, I have to first define the preferences. Click on a preferences and go to structural and say okay. Then you go to the preprocessor. In a previous class, we have discussed you how to define the element type and all. So under element type, click on a add, edit or delete. And here you can say add. And there you can click on the element, link. And the element type is 3D finite strain 180. I'll say okay. So now the element type is defined. I'll close this. I'll go to the real constant. So since the real constant, the cross section area of all the members are same, so I will define only one real constant. So it is 0.1 meter square. So if I convert that into a mm, it will be a 100 mm square. So I'll say okay. So close this. Then I'll go to material properties. Under material properties, I'll go to the material models, and under material models, click on a structural, linear, elastic, isotropic material. And the Young's modulus is 210 gigapascal is there. So I will write it in terms of a megapascal as 2.1 into e raised to plus 5. And Poisson's ratio is 0.3. And I will say okay. So now the material is defined. I have to now define the coordinates of the joints. So to do that one, I'll go to the modeling. Under that, click on the create, click on the nodes, and click on a inactive coordinate system. So I will start with the 0, x0, y0, z0 coordinate. I'll say apply. And to know the second coordinate, just refer the PPT, and it is showing a 4 meter. So 4 meter, I should convert that into a mm. So it will be a 4000 mm. So I will give this as a 4000 mm. I'll say apply. So you can see that the third point is, so in x direction it is 4000, in a y direction it is 3 meter, in the sense 3000. So I will create another node at 4000 in x direction, 3000 in a y direction. I'll say apply. So now the third node is created. The fourth node will be this. So it is x0, y is 3000. So I will give this as a 0, y is 3000 and z is 0. I'll say okay. Now I have defined the nodes. To define the elements, I have to connect a node 1 and node 2. That is one element. Node 2, node 3, second element. Node 1 and node 3 is a third element. And node 4 and node 3 is a fourth element. So just you have to follow this sketch. So to create an element, I'll go to the elements. Under that, I'll go to the element attributes. And we know that I am assigning the element type. While assigning the element attribute, it should have a what is the type of an element, what is the type of a material, and what is a cross section, that is real constant. So I have given all this and I'll say okay. So click on the auto number, go through the through nodes, and here you can select the first node and second node and say apply. The first element is created. The second element is 2 and 3. I will say apply. And the third element is 1 and 3. I'll say apply. So the fourth element is 4 and 3. I'll say okay and come out of that. Now I have to define the boundary conditions. So to define the boundary conditions, go to the loads here, click on the define loads. Under define loads, go to the apply, and here it is a structural loads. So click on the structural and displacement. Under a displacement, I will fix these two nodes, node 1 and node 4, and I'll say okay. So I have to fix those in all degrees of freedom. I will click on all DYF and I'll say okay. So you can notice that the triangular notations are the symbols that they are fixed. And also, if you see the PPT, here in the problem definition, there is a roller support. So to define that roller support, again, I have to click on this structural displacement under nodes, and I'll click this and I'll say apply. So under this, what is the roller support? So roller support means it is not allowed to move in a y direction, but it is allowed to rotate or roll over across the y direction, x direction. So in the sense, I have to fix only the uy. Uy stands for the translation degrees of freedom. So if it is a ry, it is a rotation. So I am not constraining the rotation here. So in the sense, I have to give only uy. Suppose if I click on all DYF, then I will not be representing the roller support here. So I have to deselect this all degrees of freedom and only give a uy, and I'll say okay. So you can see that only the y translation is fixed at this node. So in the sense, this node is not allowed to drop in this way, but it can move along the x direction either in x negative or x positive. It depends upon the load I am applying. So once the boundary conditions are fixed, I have to apply the force. So force, I will click on the force for a moment, and then I will click on the node, and from the PPT or from the problem definition, what it is saying, there is a 2500 Newton applied in a negative y direction at a node 3. So I will click this node and I'll say apply. So I have to select this as a Fy and give a minus 2500 and I'll say okay. So you can see that arrow mark indicating a downward direction. Then I will select this node 2, and I'll say apply. And here from the PPT, there is a 2000 Newton force applied in a x direction, positive x direction. So I will select this as the Fx, and then I will give this as a 2000 Newton and I'll say okay. So in the sense, this structure has a two external loads, one in a y direction and another in a x direction. Now the load definition is done, boundary conditions are defined, the preprocessor is done. I have to go for the solution Under the solution, click on the solve, click on the current ls, and I'll say okay. So you can see that once it is solved, it will give a message as the solution is done. I'll say close this and close this window and go to the post processing. Under post processing, you have to click on the plot results, deformed and undeformed, and click on this deformed plus undeformed and see okay. So you can see that these two nodes are not allowed to move. When I apply a load here, so it will undergo a displacement in negative y direction, and also because of this force in x direction, there is a extension, and the dotted white line is nothing but a undeformed. So you can see that it is not, this node is not allowed to move in a y direction, but it is allowed to move in a x direction because of the roller support. Okay, so this is about the problem with the truss elements. So if I want to see the nodal solution, click on the nodal solution, degrees of freedom, and I'll say displacement vector, and I'll say okay. So you can see that how the displacement contour plot looks like. Okay. Similarly, if you want to see the stresses, you can click on the element solutions, stresses, one stresses, and say okay. So you can see that stress plots also. Okay, so this completes the problem, and I will save this file as a same whatever we have. It is a 4-bar truss member. I'll say okay. So it is asking, it is already existing. Do you want to replace? Yes. So this is the fourth problem. So next we will go for the other problem with a similar kind of truss element. Only the boundary conditions are changing and the loads are changing. So here what it is, I have to create a node 1 here at a 0, 0 coordinate, and node 2 will be 750 mm and 500 mm in a y direction, and node 1 as a 500 from this reference. Okay, so again the area is 0.1 meter square and 5 kilonewton or 5000 Newton. Okay, so with this, I will start with a new file. So I'll say file, clear and start new. Don't read the file and say okay and say yes. So now the fresh window is available. So I will save this as another file. I'll save it as cantilever truss. So I will give the name as a cantilever truss, and I will go to the preferences. Under preferences, click on a structural, say OK, and under a preprocessor, click on element type, add, edit or delete. Under this, you click on add, select the link 3D finite strain 180 and say OK. So close this. Now you define the real constant. It is the same process what we have done for the previous. So for this element, you define a real constant as 100 mm square, and I'll say okay. Close this, and then I'll go to the material properties, material models, structural, linear, elastic, isotropic. So here 2.1 E5, and this one is 0.3. I'll say okay. So close this, go to the modeling. Under modeling, you go to the create, and under that, click on nodes in active CS mode, and I will keep everything as 0, x0, y0, z0, and say OK. So the second point is x is 750 mm, y is 500 mm, and I'll say OK. And the third point is 0, 500, and this one. I'll say OK. So now now I will define a element. So to define an element, I'll go to the element attributes. Under this, I will assign the link 180, material number, and constant, real constant number. I'll say OK. And under this, click on the auto numbered through nodes. So the first element is from 1 and 2. I'll say apply. The second element is 3 and 2. I'll say OK. So now the definition is done. Now I have to fix the loads. So I'll go to the loads. So under close this modeling and you go to the loads. Under that, define loads, apply, structural, displacement, nodes. So you fix this and this node and say OK. And instead of this, I have to make it as all degrees of freedom instead of a UI. So I'll say OK. So after that, I'll apply a load. Load on nodes is equal to select this node number 2 and the load is 5000 Newton from here. So I'll say apply. It is Y direction. I'll select 5000 and say okay. See, it has taken in a upward direction. So actually it should be minus 5000. Okay. So if you want to delete that load, you have to go to the load and delete structural and force, select on the this node and say okay. Say FY and say okay. So now it is deleted. I have to again apply it. Go to apply, structural, on node, select this and say okay. And it should be minus 5000 and say okay. So now it has taken a correct direction. So after I apply the load, I'll go to the solution, solve it. So once you get this message as the solution is done, you can go for the post processing. Under post processing, you go to the deformed plus undeformed and click on this. So you can see the blue line is a deformed and white line is a undeformed. So if I want to see the contour plots, click on the nodal solution and displacement vectors and say okay. Similarly, the element solution can go for the to see the stresses. Okay. So this completes the other problem, cantilever problem. And again, I will save it as cantilever truss and overwrite it. Okay. So this completes the other 2 problems. Totally now I have solved 5 problems. Okay. So in the next class, we will do the problems on the beam. Okay. So I will close the session here now. So if you have any queries, we can discuss.